We live inside a picture painted by light, and we trust that picture almost without thinking. If something cannot be seen, we treat it as absent. If it cannot be touched, we assume it cannot shape the world. And yet so much of reality works in the opposite direction. Quiet forces, invisible structures, and hidden rules that leave their fingerprints without ever showing their face. Out in space, this limitation becomes more than a curiosity. It becomes a boundary. We look at galaxies as if they are islands of stars drifting in a dark ocean. We measure their glow, we chart their shapes, and we try to explain why they hold together at all. But the deeper we look, the more the universe seems to be supported by something we cannot directly see, something that behaves like weight without having a clear source. Tonight, we'll move slowly through that unseen architecture, not as a puzzle to be solved quickly, but as a landscape to be entered. By the end, the idea of dark matter won't feel like a single strange claim. It will feel like the result of following evidence as far as it can go and noticing what refuses to disappear. And it begins with the simplest assumption we make when we look up at a galaxy. A galaxy looks, at first, like an answer rather than a question. It presents itself as a finished thing, a soft whirl of light, a disciplined curve of arms, a quiet center where stars seem to gather as if they have agreed on where to belong. From a distance that makes individual suns collapse into a single glow, it feels stable. It feels settled. And because it is made of light, it invites a simple assumption: that what shines is what matters, and what matters is what we can count. But a galaxy is not held together by beauty. It is held together by weight. Not the familiar weight of an object in your hand, but the deeper meaning of weight in space. The ability to shape motion, to bend paths, to keep a restless collection of stars from drifting apart. In the dark between stars, gravity is the only long-term architect. It is the quiet rule that turns scattered matter into structure. If you begin with the visible parts, the stars, the cold gas, the thin dust lanes, you can add them up. You can turn their light into an estimate of how much matter must be there to produce it. Astronomers learn to do this with care because different stars shine differently. Some are bright and short-lived, some are dim and long-lived. A galaxy can hide much of its mass in faint stars that barely announce themselves, or in cool gas that glows only in special wavelengths. So the accounting is not naive, it is patient. It includes what the eye cannot see unaided. And still, even with that caution, something does not line up. The first hint arrives not as an image, but as a speed. A star orbiting in a galaxy is not free. It is in a long, steady fall around a center it never reaches. Its path is a compromise between motion and gravity, between the urge to fly outward and the pull inward that keeps it bound. In our own everyday world, you can sense the logic. The farther you are from the source of a pull, the weaker that pull becomes. A planet far from the sun moves more slowly than one close in, because gravity has less grip at that distance. This is not a metaphor. It is a measured pattern in the solar system, a kind of quiet arithmetic the universe repeats. So when astronomers look at other galaxies, they bring this expectation with them. If most of a galaxy's mass is concentrated where most of its light is, toward the center, then stars farther out should orbit more slowly. The bright inner region would behave like the heart of the system, and the outskirts would move with a gentler pace. To test this, you do not need to track an individual star for millions of years. You measure the overall motion of many stars and gas clouds using the shifting of spectral lines, small changes in light that reveal whether something is moving toward you or away from you. The galaxy becomes a map of velocities, painted not in color, but in Doppler shifts. And when those maps began to fill in, the expected pattern did not appear. Instead of slowing down, the outer parts of many galaxies kept moving fast. They moved as if there were far more mass than the starlight could justify, not just a little more, but enough to dominate the galaxy's gravitational field. The rotation curve, as it came to be called, did not decline with distance the way the simplest model predicted. It flattened. It held steady, stubbornly, far beyond the bright disk. It is difficult to fully feel what that means without slipping into drama, because the finding is so quietly disruptive. A galaxy is not a static object. It is a dynamic, moving system, with billions of bodies, each tracing a path determined by the total gravity around them. If those bodies are moving too fast for the visible mass, then either the gravity is stronger than it should be, or there is more mass than the light suggests. There is no comfortable third option. If you take the light at face value, then many galaxies should be flying apart. Their outer stars, moving at those speeds, would not remain in long-term orbits. Over cosmic time, the structure would unwind. The galaxy would thin and disperse, like a cloud that cannot hold its shape. Yet when we look across the sky, galaxies persist. They are not rare accidents, they are common, they are ancient. Their spiral patterns, though not permanent like a solid object, have endured long enough to be part of the universe's regular architecture. So the question becomes unavoidable: what is providing the missing grip? One response is to assume we have underestimated the amount of ordinary matter made of atoms, the same kind that forms planets and people. Perhaps galaxies are filled with dim stars too faint to count, or with cold objects that emit almost no light, or with vast reserves of gas and dust that are difficult to detect. This is not an unreasonable thought. In astronomy, much of reality is hidden simply because it does not shine in visible wavelengths. A cloud of hydrogen in deep space may be nearly invisible to our eyes, but it can reveal itself through radio emission. A cool brown dwarf can slip through optical surveys and only appear in infrared. The universe is full of such subtle presences, and for a time, the possibility of missing ordinary matter was explored carefully. Could the halo of a galaxy be packed with faint, compact objects, dead stars, small stars, dark planets, collectively adding up to the unseen mass? Could there be vast amounts of gas in forms we had not accounted for? But every attempt to fill the gap with familiar matter ran into limits. Too many faint stars would still leave signatures in the light we receive and would affect the chemical history of galaxies in ways that could be checked. Too much gas would not remain entirely silent. It would absorb, emit, or interact. Compact objects in large numbers would reveal themselves through gravitational microlensing, tiny momentary brightening events as they pass in front of background stars. Searches found some, but not nearly enough to explain the whole missing mass. The deeper the measurements went, the clearer the pattern became. The missing weight did not behave like a hidden collection of ordinary things. It behaved like something else, something distributed in a wide halo around galaxies, extending far beyond the visible disk, shaping the motion of stars and gas as if the galaxy were embedded in an invisible sphere of mass. This idea, once it is stated, can sound like a story, but it is not born from imagination. It is born from a refusal to let the numbers drift apart. And galaxies are only the beginning. Beyond the graceful spirals and elliptical glows, the universe organizes itself into groups and clusters, communities of galaxies bound together by their mutual gravity. In these regions, galaxies are not isolated islands. They orbit a shared center, move through hot, thin gas, and interact over billions of years. If you want to test the strength of gravity on a larger scale, you can look here, where the motion is collective. The same logic applies. If you can estimate how much mass is present from the light of the galaxies, you can predict how strongly they should be bound. If the cluster contains only what we see, the galaxies should move at certain speeds. If they move faster than that, then the cluster must contain more mass than the light indicates, or else it would not hold together. When astronomers measured the velocities of galaxies in clusters, they found, again, that the motions were too fast. The clusters seemed to require far more mass than the galaxies and the visible gas could supply. The discrepancy was not confined to the delicate outskirts of spiral galaxies. It appeared in these grander systems too, where the scale is larger and the dynamics are harder to dismiss as local quirks. In a sense, clusters make the problem more severe because they add another visible component, a vast reservoir of hot gas between the galaxies. This gas is so hot that it emits X-rays, and it can outweigh the stars in the cluster. For a moment, it might seem like the missing mass has finally been found in a form we simply could not see with optical telescopes. But even after counting the gas, after adding stars, dust, and everything luminous or detectable in known ways, the cluster still comes up short. The gravity implied by the motions still demands more weight. What remains is not a small correction, it is a dominant component. It helps here to let the mind settle into the scale of the claim. The missing mass is not an extra layer of dust. It is not a hidden population of dim stars that would fill in the last few percent of a budget. It is a framework that seems to outweigh the visible universe in many places, holding galaxies in their orbits and clusters in their cohesion. The starlight becomes, in this picture, a thin luminous frosting spread over a deeper structure. And that deeper structure does not announce itself directly. It does not glow. It does not scatter light in the way dust does. It does not emit radiation like hot gas. It reveals itself only by the way it pulls. That is why the phrase dark matter emerged as a kind of placeholder with discipline. It does not claim to know what the substance is. It only names what the evidence suggests. Matter that is dark, not in color, but in its refusal to shine. If the idea feels unsettling, it is partly because it reverses a comfortable hierarchy. We tend to think that the bright parts of the universe are the main story, and the dark is merely empty space between. Dark matter suggests a different world. The bright parts may be the decoration, the dark may be the architecture. And the more carefully astronomers measured, the more that architecture seemed to be consistent across many different galaxies. Rotation curves flattened, not in one place, but in many. Clusters required extra mass not as a rare exception, but as a recurring rule. Different methods, different instruments, different objects, and the same quiet deficit. At this stage, the simplest human response would be to insist that the measurement must be wrong. Perhaps the distances are misjudged, the light misinterpreted, the velocities misread. Perhaps the models are too simple. Perhaps galaxies are stranger in their internal behavior than we imagine. And of course, scientists did not accept the implication lightly. They questioned the data. They refined the techniques. They tested alternative explanations. The strength of the dark matter story is not that it arrived triumphantly. It is that it survived careful attempts to remove it. As the evidence accumulated, the question shifted. It was no longer, is there missing mass? That part began to look like a stable observational reality. The question became, what kind of missing mass could be so widespread, so patient, and so quiet? The sky, meanwhile, continues to offer its calm image. Galaxies hanging like lanterns in a black sea, clusters scattered like constellations of constellations. It is tempting to let the beauty of it become the conclusion, to think we have seen enough simply by looking. But the motions tell a different story. They whisper that the visible universe is riding on something deeper. And if that is true, then every star we see, every glowing spiral arm, every distant smudge of light, may be tracing the shape of an invisible weight we cannot yet hold in our hands. The strange thing about missing weight is how quickly it stops feeling like a single anomaly and starts feeling like a law. Once you accept, even provisionally, that galaxies move as if they contain far more mass than they display, you begin to notice that the universe is offering the same message in different dialects. Not always through the speed of stars, not always through the cohesion of clusters, but through the way light itself travels through space, through the subtle ways the sky seems to lean, bend, and smear when something heavy sits in the path. Light, in everyday life, behaves like a straight line. It leaves a lamp, crosses a room, reaches a wall. Our brains build much of their certainty from this. Straight lines are reliable. They suggest that space is a neutral stage, and objects are merely actors moving on it. But in the universe, space is not always neutral. Gravity is not just a pull between objects. It is also, in a deeper sense, an influence on the geometry through which objects and light must move. A massive body changes the paths available around it. It changes what straight means. This is not something that must be believed as a philosophy. It can be tested. The consequence is simple. If a large mass lies between us and a distant source of light, that light can be deflected. The distant object may appear slightly displaced. In stronger cases, it may be stretched into arcs, multiplied into ghostly images, or arranged into rings. The sky can act like a lens, not because there is glass, but because there is weight. This becomes a remarkably powerful idea because it offers a way to map mass without asking whether that mass shines. You do not need to see the matter directly. You watch what it does to the light behind it. You look for distortions, for the gentle statistical shearing of background galaxies, for the quiet asymmetries that appear when many faint sources are averaged together. And when those mass maps are made, when clusters are weighed by the way they bend light, the same conclusion appears again. The visible matter does not supply enough weight. The luminous galaxies, even combined with the hot X-ray gas that fills the cluster, account for only a portion of the gravitational influence. The lensing suggests more. It suggests an unseen component extending beyond the bright regions, shaping the curvature of space on scales larger than any individual galaxy. Here, the evidence gains a kind of calm independence. Rotation curves tell one story through motion. Cluster dynamics tell it through collective behavior. Gravitational lensing tells it through geometry. Each method has its own uncertainties, its own potential mistakes, and yet, again and again, the same absence shows up in the accounting. The missing weight is not tied to a single technique. It appears as a persistent gap across the ways we know how to measure the cosmos. There is a particular kind of quietness in this. No single observation forces a dramatic conclusion. Instead, the conclusion is shaped by repetition. It is formed the way coastlines are shaped, by the same gentle pressure applied over and over. And once you begin to accept that the universe contains a large amount of unseen mass, a new question emerges naturally. Where is it? Not where in the sense of an address, but where in the architecture of space? Is it scattered evenly, like a fog? Is it concentrated in the same places as stars? Does it form structures of its own? The early clues suggest something subtle. Dark matter, whatever it is, seems to form halos around galaxies. It seems to surround them, extending far beyond the visible disk. It is not simply hiding in the bright parts, it is arranged differently. And that difference matters, because it changes the story of how galaxies and clusters could have formed in the first place. A galaxy is not just a collection of stars that happened to gather. It is the endpoint of a long process, matter cooling, clumping, rotating, fragmenting, forming generations of stars, recycling gas through supernovae and winds, building structure over time. Ordinary matter, atomic matter, has a complicated life. It interacts with light, It loses energy by radiation. It collides, heats, cools, and forms patterns that can be disrupted by feedback from star formation. If dark matter behaved the same way, it would not remain dark. If it interacted strongly with light, it would glow or absorb. If it collided and cooled like gas, it would form a thin disk, settling into the same plane as the stars. But observations suggest it does neither. Dark matter seems to remain spread out, forming a broad, roughly spherical halo, rather than collapsing into a luminous, rotating sheet. This difference is more than a detail. It hints at a kind of matter that mostly ignores the electromagnetic world. It does not radiate away energy efficiently. It does not clump into bright knots through the same processes that create stars. It can gather gravitationally, but it does not easily shed its motion through collisions. It can form a scaffold, but not the decorations. The galaxy then becomes a layered object, a visible disk of stars and gas embedded within an invisible halo whose mass dominates the outskirts. The starlight marks where ordinary matter managed to cool and settle, while the hidden mass marks where gravity has been patient and broad. With this picture, some things that were puzzling begin to look almost inevitable. The flattened rotation curves, for instance, make sense if there is a large reservoir of mass extending outward. The outer stars are not orbiting a small, bright center alone. They are orbiting within a much larger mass distribution that continues far beyond what we see. Clusters, too, become less mysterious in their cohesion. They are not held together only by the sum of their visible galaxies and gas. They are embedded in a deeper gravitational environment, one that can bind the whole system. Yet even as the idea begins to organize the evidence, it does not feel like a closed explanation. It feels like a name for a missing piece. And names can be deceptive because they sound like understanding. Dark matter is a label shaped by what it does not do. It does not shine. It does not emit or absorb light in the usual ways. It does not participate in chemistry. It does not build planets. It does not form living cells. It does not make the familiar world. The phrase tells you more about our instruments than about the substance itself. It tells you we have looked in the obvious place, light, and found a deficit. It tells you the universe is pushing back against a human habit, the habit of treating the visible as the real. In the decades that followed the first strong measurements, scientists did what they always do when faced with a persistent discrepancy. They tried to make the discrepancy go away, and they tried to understand how it might be telling the truth. Some pursued the idea that gravity itself might behave differently on very large scales or at very low accelerations. If the law of gravity subtly changes in regimes we do not encounter in the solar system, then perhaps galaxies could rotate as observed without extra mass. This line of thought is not a refusal of evidence. It is an attempt to explain the evidence with a different assumption. It asks whether the missing weight is not matter at all, but a sign that our map of gravity has incomplete edges. Other researchers treated dark matter as a new ingredient, something not yet identified in particle physics, something that does not fit into the catalog of ordinary atoms. In this view, the missing mass is literal mass, carried by particles that rarely interact with normal matter except through gravity. Such particles would be difficult to detect, not because they are mystical, but because they slip through ordinary materials as neutrinos do, only more so, leaving almost no trace. In the calm space between these approaches lies the heart of the mystery. We can infer the presence of something, but we do not yet know its identity. And still, the universe continues to build with it. When astronomers and cosmologists simulate the growth of structure over cosmic time, they begin with a nearly smooth early universe and allow gravity to work. Small variations in density grow, drawing matter inward. Over billions of years, those small differences can become galaxies, clusters, and the cosmic web. In such simulations, Ordinary matter alone struggles to build structure in time because it interacts with radiation in the early universe and resists clumping until the universe cools enough. But a dark component that interacts mostly through gravity can begin collapsing earlier, creating wells into which ordinary matter can later fall. The result is a universe where invisible structure forms first, and visible structure follows. This is a profound reversal of intuition. We're used to thinking of the visible as primary. In this story, the visible is late. The stars we see are not the first framework. They are the luminous consequence of an earlier, unseen arrangement. If this is correct, then every bright galaxy is sitting inside a dark halo not as an afterthought, but as a condition. The dark matter shaped where galaxies could form, how they could grow, and how they could arrange themselves into larger systems. The cosmic web, the filaments and voids that surveys reveal when they map the positions of galaxies across huge volumes, may be tracing an even deeper web of unseen mass. Even without images, you can sense this structure by imagining motion on the largest scales. Galaxies are not merely drifting randomly. They are flowing along gravitational gradients, subtly pulled toward denser regions, drawn into clusters, leaving behind emptier voids. Over immense time, gravity sculpts the distribution, and the distribution tells you where the weight is. When we speak of the universe expanding, it can sound like everything is simply rushing away. But within that expansion, local gravity still competes. It still gathers. It still binds. The unseen mass is part of how that competition plays out. And then, inevitably, the story reaches a quiet edge. Because at some point, after the evidence has been gathered and the framework has been built, the simplest question returns, unchanged. What is it? It is possible, in the face of that question, to feel that science has failed. But the truth is gentler. Science often lives comfortably with unknowns, as long as those unknowns are clearly outlined. Dark matter is not a fog of ignorance. It is a sharp shape of ignorance. It is a boundary drawn by measurement. The boundary is clear. There is extra gravitational influence that cannot be explained by the matter we can see and count in ordinary ways. That influence is structured. It clusters around galaxies and clusters. It shapes the motion of visible matter and the bending of light. What remains unclear is the nature of the substance, or whether it is substance at all. And yet, even without a final identity, the idea already changes how we understand our place. We are made of the rare kind of matter that can shine, cool, and build complexity. We are made of atoms that can form molecules, that can hold together in intricate arrangements, that can create chemistry and life. The universe, however, may be dominated by something that does none of this, something that forms the gravitational backbone while remaining indifferent to the luminous world. There is a humility in that. Not a humiliation, but a quiet correction. It suggests that what is most important for the universe's architecture may be almost completely silent to our senses. It suggests that the cosmos is not obligated to be visible. And it suggests something else, equally calming. That human knowledge has always advanced by learning to trust indirect traces. We learned about atoms before we could image them. We learned about distant planets before we could photograph them. We learned about the interiors of stars by studying the light they emit. In each case, the evidence came first, and understanding followed later, sometimes by decades, sometimes by centuries. Dark matter, in this sense, is part of a familiar pattern. The universe has left marks. We have noticed them. We have given the marks a name. The name holds a place open for a deeper explanation. So when you look at a galaxy again, whether as a photograph, a pale smudge through a telescope, or simply as an idea, you can let the light remain what it is, a surface. Beneath it is a structure that does not announce itself, but does not loosen its grip. The stars continue their orbits as they have for billions of years, guided by a weight that does not glow. And in that steady motion, the universe offers one of its most enduring lessons: that reality is often larger than the part of it that shines. There is a particular kind of certainty that arrives through the eyes. In the everyday world, sight is enough. It tells us where the ground is, where the edge of a table begins, whether a doorway is open or closed. It gives distance, shape, and warning. We learn early to trust it, and because it is so reliable at human scale, we quietly allow it to stand in for reality itself. What we can see feels real. What we cannot see feels doubtful. And yet, even on Earth, the most decisive parts of existence are not visible. The air that fills a room has weight, but it is transparent. A magnetic field shapes a compass needle without having a color. The pull of gravity holds your body to the floor without casting a shadow. These forces are not hidden in a dramatic way. They are simply outside the range of the senses that evolved to help a small animal survive in daylight. When we look outward into space, this limitation stops being a philosophical idea and becomes an operational problem. The universe is not obliged to display itself in the narrow band of light our eyes can detect. It does not arrange its truths according to the comfort of human perception. Most of what exists out there is cold, thin, dark, and distant. It does not announce itself with brilliance. It only leaves consequences. So the first step is not to force the cosmos into the shape of our intuition, but to notice what our intuition tends to do when it is tired, when it is faced with scale, and when it is offered only fragments. One of the simplest biases is to treat brightness as importance. A city at night, seen from above, seems to reveal where the life is. But the lights are only a surface signal. They do not show the water pipes, the concrete foundations, the quiet weight of the buildings themselves. In the same way, the bright stars in a galaxy are only the visible crest of a deeper system. The mind, however, pulls toward the glow. It wants the brightest parts to be the main story, because brightness is easy to measure and easy to imagine. In astronomy, this becomes a kind of trap. A galaxy's center blazes with light, so we assume it must also hold most of the mass. The outskirts are dim, so we assume they are empty. Yet dim does not mean absent. In the universe, faintness often means only one thing: that matter is not radiating in a way we can easily capture. There is another bias that follows close behind: the expectation that empty space is truly empty. To the eye, space looks like a black background with a few scattered points. Even when a telescope reveals more points, the darkness remains dominant. It is natural to imagine that the darkness is nothing, that the stars are everything, and that the universe is mostly absence. But the darkness is not a substance. It is a limitation. It is the absence of signal in a particular kind of detector. Between the stars in our own galaxy, there is gas so thin it would be called a vacuum in any ordinary room, but it still adds up across vast volumes. There are dust grains that drift like slow snow. There are fields and particles that pass through matter as if it were mist. And on the largest scales, there are structures so diffuse that they would never be seen as objects at all, only inferred through the way they influence light and motion. The mind does not naturally handle this. Our instincts are tuned to environments where emptiness is rare and distance is small. When something is far away, we treat it as less relevant. When something is thinly spread, we treat it as negligible. But in space, distance and thinness are not excuses for insignificance. They are the normal state of things. Scale itself introduces a deeper distortion: the failure of intuition to feel time. A galaxy rotates slowly in the way continents drift. To say it takes hundreds of millions of years for a single orbit is not to give a useful emotional picture. It is to announce that this motion lives outside the rhythm of human thought. Our brains are good at tracking change over seconds, minutes, seasons. We are less good at tracking change over eras. When we look at a galaxy, we see a still image and assume stillness. But what we are seeing is a frame taken from a moving film, whose length is almost beyond language. This can make the universe feel calmer than it is, or more stable than it is. The mind confuses slowness with permanence. It assumes that because change cannot be watched directly, it is not happening. In reality, the galaxy is in continuous motion, and its stability, its ability to remain a coherent system, is something that must be explained, not assumed. Then there is the bias that comes from living inside gravity. On Earth, gravity is so constant that we barely notice it. We experience it as weight, as a downward pull, as the reason water stays in a glass. But this is only one face of gravity, shaped by standing on a planet. In space, gravity is not simply down, it is inward, outward, sideways, curved. It is a relationship between mass and distance, acting across emptiness without needing contact. When we picture gravity as a force like a rope or a hand, we are already simplifying. When we picture it as something that only matters near large visible bodies, we simplify even more. The universe punishes these simplifications, gently but firmly. A star can orbit in darkness, because gravity does not care whether the source is lit. A galaxy can remain bound because gravity adds up, even when the mass is spread into a halo too faint to announce itself. A cluster can hold together because the real center of mass is not necessarily marked by the brightest region. To accept this is to accept a different style of knowing. Not knowing by seeing, but knowing by tracing. A footprint in snow tells you about an animal you have not witnessed. A wake on a lake tells you a boat has passed, even if the boat is already beyond the bend. In science, the same principle becomes a discipline. You measure effects, you compare them to expectations, and you infer the hidden cause that best explains the pattern. Astronomy is, by necessity, an art of inference. Almost everything we know about distant objects comes from light collected at the end of a long journey. That light is thin, delayed, and filtered through intervening space. It carries information, but never the whole thing. From it, we extract distance, speed, composition, temperature. We build models that connect what is seen to what must exist. The danger is not inference itself. The danger is forgetting that inference is what we are doing and slipping back into the comfort of direct perception. There is a quiet psychological reason the idea of unseen mass is hard to hold. It threatens a familiar sense of control. If the universe contains a dominant component that does not speak to our senses, then our picture of the cosmos has been drawn with a missing layer. It suggests that the map we build from light is incomplete in principle, not merely in detail. This can feel like standing in a well-lit room and realizing the walls extend farther into darkness than you thought. The room is still real, the light is still accurate, but it no longer defines the whole space. At the same time, the mind resists the opposite error, the temptation to treat the unseen as mystical. When something cannot be directly observed, imagination rushes in. It supplies shapes, intentions, and stories. It turns unknown into otherworldly. This is another bias, and it is just as misleading. The unseen components of the universe are not hidden because they are magical. They are hidden because our senses and instruments evolved and were built around a narrow slice of reality. When we expand the instruments, new parts of reality appear. When we expand the methods, new traces become legible. This is why modern astronomy is not a single way of looking, but many. Visible light shows starlight and the glow of hot gas. Infrared reveals cooler dust and faint stars. Radio waves trace cold hydrogen and energetic particles spiraling in magnetic fields. X-rays expose gas heated to millions of degrees. Each band is like a different sense, and together they build a more complete portrait. Yet even this expanded portrait is still bound by a deeper constraint. The universe may contain matter that interacts only weakly with all forms of light. If so, then no telescope, no matter how sensitive, will simply photograph it in the usual way. The mind must accept that some things will remain invisible, not because they are beyond science, but because the method of seeing is the wrong tool for that job. The most reliable way forward, then, is to treat light not as a picture, but as a messenger. A messenger can be honest without being complete. It can report what it encountered, not what it missed. Light tells us where energy was emitted or absorbed. It tells us about temperature and composition. It tells us about motion through shifts in frequency. It does not tell us the full inventory of mass. Once this is internalized, the earlier discrepancy in galaxies becomes less like a paradox and more like a reminder. It reminds us that the universe's deepest structures may be written in a language other than brightness. There is also a subtler bias at work, one that lives not in the senses, but in the stories we prefer. We like explanations where the cause resembles the effect. If stars are moving quickly, we look for more stars. If a galaxy is heavy, we look for heavy luminous objects. We prefer additions of familiar things because they preserve the world we already recognize. But nature is not obligated to solve our problems with familiar ingredients. It can introduce a new kind of matter, or reveal a new regime of gravity, or show that our assumptions about what counts as normal were shaped by living in a small, bright corner of a larger reality. To sit with that possibility is not to abandon clarity. It is to make room for it. And this is the calm pivot of the story. The point where the universe asks us to loosen our grip on what sight alone can guarantee. Not to distrust what we see, but to stop treating it as the full account. Because the universe is speaking through motion, through structure, through the quiet choreography of objects that obey gravity whether or not their source is lit. It is offering evidence that can be weighed, compared, and followed. And once the mind becomes comfortable with that style of knowing, the darkness stops being a void. It becomes a field of potential information, waiting to be read by methods more patient than the eye. The mind changes slowly, but once it shifts, it rarely returns to its original shape. After the first recognition that sight is not the same as knowledge, the universe begins to look less like a picture and more like a process. What matters is no longer only where light appears, but where influence accumulates. Motion, distortion, and balance become the new clues. The cosmos stops being something that simply shows itself and starts becoming something that must be interpreted. This is not an abstract exercise. It is a practical necessity because much of the universe announces itself only through secondary effects. Even stars, which feel like the most obvious objects in the sky, are known in this way. We do not touch them. We do not sample them directly. We infer their interiors from the light that escapes, filtered through layers of plasma and time. In this sense, astronomy has always relied on disciplined imagination, an imagination constrained by measurement. Dark matter, then, does not represent a break from how science works. It represents a continuation of its most careful habits. One of those habits is statistical patience. When individual objects are too faint or too distant to reveal a pattern on their own, astronomers look for trends across many systems. They average. They stack. They compare. A single galaxy's rotation curve might be noisy, shaped by local quirks. Hundreds of galaxies, examined together, begin to reveal a shared structure. Weak gravitational lensing around a single cluster might be subtle, barely above the level of uncertainty. Across thousands of clusters, the signal becomes unmistakable. This way of knowing can feel unsatisfying to the intuition. It does not offer a single dramatic image, it offers a slow convergence. The confidence comes not from one striking result, but from the refusal of many small results to contradict each other. The human mind, however, evolved to respond to singular events. We remember the unusual, the bright, the sudden. Patterns that emerge only through accumulation are harder to feel. They require trust in method rather than trust in impression. This tension helps explain why invisible mass can feel more speculative than it is. The evidence does not arrive as a spectacle, it arrives as agreement between independent lines of reasoning, each imperfect on its own, but coherent together. There is also a deeper cognitive challenge. Accepting that the universe may be dominated by something we cannot easily relate to ourselves. Human understanding is shaped by analogy. We explain the unfamiliar by reference to the familiar. We understand atoms by comparing them to systems we know. We understand gravity by comparing it to pulling and falling. When faced with something that resists analogy, the mind reaches for extremes. It either dismisses the idea or inflates it into something mysterious and untouchable. Dark matter invites neither response. It asks for restraint. It does not behave like ordinary matter, but it also does not violate physical law as we understand it. It follows gravity. It contributes to mass. It participates in structure formation. It simply does so without the electromagnetic interactions that make matter visible, warm, and chemically expressive. This absence of interaction is not a flourish, it is a constraint. If dark matter interacted strongly with light, we would see it. If it collided frequently with ordinary matter, we would have detected it in laboratories or in the behavior of stars and planets. Its silence is part of the evidence. From a psychological point of view, silence is difficult to accept as information. We are trained to listen for signals, not for their absence. Yet in science, absence can be just as revealing. The lack of friction tells you something about the medium. The lack of emission tells you something about interaction strength. The lack of disturbance in sensitive experiments tells you something about what is not happening. Learning to treat silence as data is one of the quieter disciplines of scientific thought. There is also a cultural habit that must be set aside. The idea that knowledge advances in clean, visible steps. In reality, understanding often advances unevenly. Evidence accumulates before explanation. Effects are cataloged before causes are named. The universe does not wait for our theories to be complete before behaving as it does. The history of astronomy is filled with such moments. The motion of planets was mapped long before gravity was understood. Stellar spectra were cataloged before the physics of fusion was clear. In each case, careful observation built a framework that theory later learned to inhabit. Dark matter fits this pattern. The framework is already there. Galaxies rotate in certain ways. Clusters hold together in certain ways. Light bends in certain ways. The cause remains under investigation, but the shape of the problem is well defined. This is an important psychological anchor. It prevents the mind from drifting into either impatience or despair. Not knowing what something is does not mean not knowing that it is. Another subtle bias the mind must navigate is the desire for closure. We like explanations that feel finished, that tie loose ends neatly. The idea that a major component of the universe remains unidentified can feel like an unfinished sentence. But the universe is not a story designed for narrative satisfaction. It is a system that reveals itself gradually, often asymmetrically. Accepting this does not weaken understanding. It strengthens it by keeping it flexible. It allows room for refinement, revision, and surprise. And there is one more quiet adjustment the mind must make. Letting go of the idea that reality must center on the conditions that allow us to exist. Ordinary matter, The kind that forms stars, planets, and life is special in many ways. It interacts richly. It builds complexity. It gives rise to chemistry and biology. It is tempting to assume that because it is the stage for our experience, it must also be the dominant substance of the cosmos. But dominance in structure does not imply dominance in expression. A framework can be simple and silent, while the details that decorate it are intricate and loud. In this view, ordinary matter is not insignificant. It is just not the whole. This reframing has a calming effect. It removes the need to place humanity at the center of the universe's composition. It allows us to be a natural consequence rather than a cosmic priority. The dark component of the universe does not diminish the bright one. It supports it. Once this mental landscape is accepted, certain questions can be approached without strain. Instead of asking why the universe hides so much, we can ask how it reveals what it does. Instead of demanding direct images, we can refine indirect measures. Instead of expecting immediate answers, we can trace constraints. The mind becomes less of a judge and more of a listener. This shift also clarifies why debates about unseen mass are not philosophical distractions, but essential to understanding how the universe works. The distribution of mass determines how structures grow, how galaxies interact, how matter flows over time. Misjudging that distribution would distort every larger conclusion. If most of the universe's mass is invisible, then any story told only with visible matter is incomplete by design. It would be like describing ocean currents by watching only the foam on the surface. And yet, even with this recognition, there remains a delicate balance. The unseen must not become a catch-all explanation, a convenient box for every unexplained observation. The discipline lies in precision, in using invisible mass only where it is required, and in subjecting the idea to continuous testing. This is why alternative explanations are taken seriously. It is why measurements are repeated, refined, and challenged. It is why simulations are compared against observation, and why discrepancies are treated as opportunities rather than failures. The universe, after all, has no obligation to be simple, but it does have a habit of being consistent. As the evidence for unseen mass persists, the human mind gradually learns a new kind of humility. Not the humility of ignorance, but the humility of proportion. We begin to sense that what we experience directly is a narrow band carved out of a much broader reality. This does not make that band meaningless. On the contrary, it makes it precious. The fact that complex, luminous, thinking matter can arise within a universe dominated by something silent and dark becomes more remarkable, not less. And in this way, the limits of seeing become a gateway rather than a barrier. They invite us to refine our tools, expand our concepts, and accept that understanding often arrives sideways. Not through what stands in front of us, brightly lit, but through what leaves its mark while remaining unseen. The universe continues to move, to bend light, to hold itself together. It does so with or without our comfort. Our task is not to force it into familiar shapes, but to follow the evidence patiently, wherever it leads. And in that patience, a quieter form of clarity begins to take shape, one that does not depend on sight alone, but on the willingness to trust the weight of what cannot be seen. Night does not only hide things, it also sharpens what remains. When the sky is dark enough, the eye begins to notice structure where it once saw emptiness. Faint bands, delicate clouds, a soft river of starlight crossing overhead. Even then, most of what is present is still beyond vision. The darkness is not a curtain. It is a reminder that light is selective, and that the universe can be full without being bright. Gravity, by contrast, is not selective. It does not ask for brightness. It does not require a surface to shine. It is patient, universal, and indifferent to the senses. It works in the dark with the same steady attention it gives to the stars. So when astronomers speak about weighing the universe, they are not speaking poetically.
They are speaking about a practical method, watching what moves, watching what bends, and letting the geometry of motion reveal what light alone refuses to show. At the center of this method is a simple idea that feels almost too plain for the scale it addresses. If you want to know how much mass is inside a system, you can look at how fast things are moving within it. A faster orbit requires a stronger inward pull. A stronger inward pull requires more mass, or a greater concentration of it. This relationship is not a preference or a human model. It is a balance written into motion itself. You can see it in a stone swung on a string, in the moon's orbit around Earth, in the way planets trace their paths around the sun. In the cosmic setting, the same balance holds, but the orbits are immense, and the objects are not tidy spheres. A galaxy is a complicated swarm. It contains stars of different ages, clouds of gas, dust lanes, spiral patterns that are not permanent objects, but long-lived waves moving through a rotating disk. Even so, the basic logic of motion remains. The galaxy cannot escape gravity, and gravity cannot hide from the consequences of its own pull. To measure that pull, astronomers begin with light, not as an end, but as a tracer. When gas moves, the light it emits shifts slightly in frequency, sliding toward the blue if it approaches us, toward the red if it moves away. These shifts are small, but they can be measured with exquisite precision. They allow a map of speed across the face of a galaxy, one side coming toward us, the other moving away, the whole system turning. The resulting curve, speed versus distance from the center, is like an X-ray of a galaxy's gravitational structure. It does not show the mass directly, but it shows what mass must be present to keep the motion as it is. In a system where most mass sits in the bright center, the curve should fall with distance, and in many galaxies, it simply does not. It levels out and stays steady, as if the mass continues far beyond the visible light. This is one way gravity speaks, through the refusal of motion to slow down. But galaxies are not the only systems where gravity can be read like this. On larger scales, clusters of galaxies provide a different kind of evidence. A cluster is not one rotating disk, but a crowded region where hundreds or thousands of galaxies drift in a shared gravitational environment. There is no neat spiral. There is only the collective behavior of many separate islands of stars. Here, the measurement is not a rotation curve, but a dispersion, a spread of velocities. If galaxies in a cluster are moving quickly in many directions, the cluster must have enough mass to keep them bound. Otherwise, the cluster would unspool over time, its members flying apart like sparks. To estimate the mass, astronomers again use light as a tracer. They measure the red shifts of galaxies, compiling their velocities relative to the cluster's average. Then, they apply a principle that appears again and again in physics. When a system is stable over long times, motion and gravity settle into a kind of balance. The faster the internal motions, the deeper the gravitational well must be. Clusters, examined this way, show the same pattern as galaxies. The mass implied by their motions exceeds the mass seen in stars and even in hot gas. The cluster behaves as if it is embedded in a much heavier structure than its light suggests. So gravity speaks again, this time through the collective restlessness of galaxies. There is, however, a limitation to relying only on motion. Motion tells you about gravity, but it also requires assumptions about whether the system is settled, whether it is in equilibrium, whether its motions reflect a stable structure or a recent disturbance. Galaxies collide, clusters merge. The universe is not always calm in the way our measurements would like it to be. For this reason, astronomers look for a more direct signature,
one that does not rely on internal balance, but instead uses the universe itself as a measuring device. This is where the story turns to the path of light. When light from a distant galaxy travels toward us, it crosses enormous distances. It passes through regions of emptiness, through filaments of gas, near stars, near galaxies, near clusters. Most of the time, it travels without dramatic interruption. But gravity, even when subtle, nudges its path. Over long distances, tiny deflections add up. If a massive object lies between us and a background source, the light's path can bend enough to change what we see. In strong cases, the background galaxy appears stretched into arcs or duplicated into multiple images. In very special alignments, it can form a near-perfect ring of light. These are not illusions. They are geometry made visible. The important point is not the beauty of these distortions, but what they allow. A map of mass that does not depend on brightness. Gravitational lensing weighs the intervening object because the amount of bending depends on the gravitational field, and the gravitational field depends on mass. If the visible matter were all that existed, the lensing would be weaker. If there is extra mass, the arcs and shears become stronger, more extended, more consistent with a deeper well. In clusters, lensing becomes a powerful conformation. The lensing mass maps often show that most of the weight is not located where most of the light is. Sometimes it sits in regions with relatively few bright galaxies, or it forms broad halos that extend beyond the luminous core. On smaller scales, lensing can be subtle, too subtle to see in a single background galaxy. But when many background galaxies are analyzed together, their shapes show a faint, coherent distortion. Their orientations become slightly aligned, as if a gentle hand has brushed them in the same direction. This weak lensing, measured statistically, reveals the presence of mass distributed across space, shaping light without shining. So gravity speaks a third time, not through the motion of stars or galaxies, but through the bending of the universe's own straight lines. And then, quietly, these different voices begin to agree. Rotation curves suggest extra mass around galaxies. Cluster dynamics suggest extra mass binding clusters. Lensing suggests extra mass that can be mapped even where there is little light. These methods are independent in their details. They rely on different instruments and different assumptions, yet the same conclusion emerges. Visible matter is not enough to account for the gravitational structures we observe. This agreement is one of the calm strengths of the case. It is not a single dramatic anomaly, it is a convergence. Still, even convergence must be handled carefully. Every measurement carries uncertainty. Every inference has edges. The discipline lies in testing those edges, in searching for places where the story might break. One such test is to compare mass measured through lensing with mass inferred from motion. If both methods yield similar results, confidence grows. If they diverge, the discrepancy becomes a clue, either to measurement error, to complex dynamics, or to something deeper about gravity itself. Another test comes from looking at systems where different kinds of matter behave differently. In ordinary astrophysical processes, gas can collide, heat up, and slow down, while galaxies, vast collections of stars, pass through each other more cleanly. If there is an additional, mostly collisionless component of mass, it may separate from the gas during collisions. In such cases, lensing can show where most of the mass went, even when the brightest gas has been displaced. This kind of observation does not identify dark matter directly, but it strengthens a specific picture, that the dominant mass component behaves unlike ordinary hot gas and does not always follow the luminous material. Beyond individual galaxies and clusters, gravity also leaves its traces in the large-scale arrangement of the universe. Galaxies are not sprinkled randomly. They form patterns, filaments, walls, knots, and vast empty voids. The distribution is uneven, like a foam or a web. This structure is shaped by gravity acting over billions of years on small initial differences in density. To understand that growth, cosmologists use simulations. They begin with a nearly smooth early universe, add tiny fluctuations, and let gravity amplify them. The resulting patterns can be compared with surveys of real galaxies. If the universe contained only ordinary matter interacting with radiation in the early cosmos, the growth of structure would proceed differently. A dark component that interacts mostly through gravity can begin clumping earlier, forming the scaffolding into which ordinary matter later falls. Even here, the evidence is still gravity-based. It is not the direct detection of a particle. It is the recognition that the universe's structures, both in motion and in distribution, behave as if an unseen gravitational component has been shaping them from the beginning. In all of this, gravity is acting like a translator. It translates invisible mass into visible consequences. It turns absence of light into presence of structure. And yet, there is a restraint that must be held on to. Gravity can tell us about mass, but it cannot tell us the identity of that mass. A scale can tell you weight, not composition. Two different substances can weigh the same and still be fundamentally different in nature. This is why the story remains open. The evidence points strongly toward hidden mass, but the evidence is still indirect. It is a shadow on motion, a fingerprint in light, a pattern in the cosmic web. The calm power of the approach is that it does not require certainty of mechanism to establish a fact of influence. The universe is heavy in ways we cannot see. We know this because the stars refuse to slow, because clusters refuse to disperse, because light refuses to travel in straight lines where mass lies in wait. Gravity does not explain itself. It simply reveals what is there.
Gravity has a way of making the invisible feel inevitable.
Once you learn to read its signatures, the universe becomes less like a set of objects and more like a set of pressures, fields of influence layered over darkness, guiding motion with a steadiness that does not need to announce itself. The night sky can still be enjoyed as a picture, but behind the picture, there is a weight map, and the weight map is often the deeper truth. Yet even this truth comes with a quiet complication. When we use gravity as evidence, we are relying on a single messenger. We are allowing one force to tell us about everything else. That is both the power and the limitation of the method. Gravity is universal, but it is also shy. It does not reveal its sources directly, it only reveals totals. How much mass seems to be present, and how that mass is distributed.
It does not tell us whether the mass is made of cold gas, compact objects, unfamiliar particles, or something stranger. It tells us only that the accounting must balance, and that the light is not enough. This is why the search for hidden mass has become, over time, a story of cross-checks. When astronomers measure a galaxy's rotation curve, they are partly measuring the behavior of stars and gas, and partly measuring their own assumptions. They must assume a distance to the galaxy, because speed estimates depend on scale. They must assume an orientation, how tilted the galaxy is relative to our line of sight, because that affects how Doppler shifts translate into true orbital speeds. They must interpret the contribution of ordinary matter accurately, because stars and gas do contribute real gravity. If those contributions are underestimated, the need for unseen mass can be exaggerated. So the work becomes careful and layered. Observers measure distances using multiple methods. They compare gas dynamics with stellar dynamics. They test whether different tracers of motion agree. They observe galaxies across a range of sizes and types,
searching for patterns that persist even when the details change. The remarkable result is not that every galaxy behaves identically. It is that the general discrepancy persists through diversity. Small galaxies, large galaxies, bright ones, faint ones. Many show the same stubborn refusal to match the mass implied by their light alone. And when the discrepancy appears in more than one way, the picture becomes harder to dismiss. Gravitational lensing, for instance, does not rely on equilibrium in the same way cluster dynamics does. It does not require the system to be settled. It measures the bending of light at the moment of observation. Its uncertainties are different, linked to the shapes and distances of background galaxies, to the quality of imaging, to the modeling of the lens geometry. But it is not fooled by internal turbulence or recent mergers in the same way motion-based methods can be. In a cluster, these differences matter. Clusters are not always calm. They grow by merging, swallowing smaller groups, stirring their hot gas into vast turbulent reservoirs. If you tried to weigh a disturbed cluster using only galaxy velocities, you might overestimate or underestimate its mass depending on the moment you catch it. Lensing provides an anchor. It reveals where the mass is concentrated even in the aftermath of collisions, when gas and galaxies are still rearranging themselves. This is where one of the most instructive cosmic scenes unfolds: the separation of what shines from what weighs. In collisions between clusters, the hot gas can slow down and heat up, glowing strongly in X-rays, marking the violent center of the interaction. The galaxies themselves, being mostly empty space between stars, pass through more easily, like flocks crossing in the night. If most of the mass were tied to the gas, then the mass map should follow the gas. If most of the mass is in a collisionless component, then the mass map should align more closely with the galaxies. When lensing maps are compared with the positions of gas and galaxies in such systems, the result can be stark. The lensing mass tends to track the galaxies more than the gas. The brightest material is not always where the strongest gravity is. This does not solve the identity of the unseen mass, but it sharpens the constraint. It suggests that whatever dominates the gravity does not behave like ordinary gas. It does not collide, slow, and pile up in the same way. It moves through the collision with a quieter persistence. In this way, gravity becomes not just a scale, but a behavioral test. It reveals not only that something is present, but how that something responds to cosmic events. There is another gravitational messenger that operates on an even older canvas, the relic light from the early universe. Long before galaxies existed, when the universe was still hot and dense, matter and radiation were coupled in a kind of luminous fog. Tiny variations in density left imprints in the distribution of that light. Much later, as the universe expanded and cooled, that light was released and has been traveling ever since, stretched into microwave wavelengths by the expansion of space. This ancient radiation carries a pattern of slight temperature differences across the sky. Those differences are not random. They encode the conditions of the early cosmos, including how much matter, ordinary and otherwise, was shaping the gravitational landscape at that time. Again, the method is indirect. No one is photographing dark matter. But gravity, even then, was influencing how matter and radiation could clump and oscillate. The pattern in the relic light becomes a fingerprint of the universe's contents. From this fingerprint, cosmologists can infer the relative amounts of ordinary matter and a non-luminous component. The conclusion that emerges aligns with what galaxies and clusters suggest. Ordinary matter alone is not enough. What makes this line of evidence especially calming is its independence in time. Rotation curves and lensing are measurements of the universe as it is now, in its mature structure. The relic radiation is a message from an era before structure formed, before stars, before planets. If both point toward the need for unseen mass, the idea begins to feel less like a patch and more like a fundamental ingredient. Gravity, in that sense, ties the story together across epochs. The same force that holds galaxies together today also left traces in the earliest light. But as the evidence strengthens, so does the responsibility to avoid overreach. Because it is possible to mistake the success of a framework for proof of a specific substance. Dark matter, as an idea, can explain many gravitational observations. That does not mean every anomaly is dark matter, or that every discrepancy is solved by adding more of it. Good science keeps the category narrow. It uses the concept only where it is demanded, and it continues to ask whether an alternative, such as a modification of gravity, could produce the same results. This tension remains part of the story. Gravity is a reliable guide, but it is also the object of our curiosity. We are using gravity to test the universe, while also wondering whether gravity itself behaves exactly as we expect in every regime. That is why some researchers look for environments where the usual assumptions could break. Very small galaxies, for instance, where accelerations are tiny and the gravitational field is weak, can serve as laboratories for testing whether gravity might subtly change its behavior. The outskirts of galaxies, where rotation curves flatten, can be seen as either evidence of unseen mass or evidence of a different gravitational rule. Here, the cosmos offers not a clear verdict, but a set of constraints. Any explanation, dark matter or modified gravity, must account for the wide range of observations, the lensing patterns, the cluster collisions, the growth of large-scale structure, the early universe imprints. Gravity is the judge, but the verdict is not delivered in a single sentence. It is delivered through consistency. And consistency in this field is hard-won. It comes from decades of refining instruments, improving surveys, expanding wavelength coverage, and building statistical power. It comes from comparing the same system through different lenses, literally and metaphorically, until the uncertainties narrow. This is the quiet strength of the gravitational approach. It does not rely on one heroic observation. It relies on a web of measurements that support each other in different ways. Even so, there remains one kind of evidence that gravity cannot provide: direct contact. Gravity can tell us that hidden mass exists and where it lies, and how it behaves in large-scale motion. But it cannot tell us what dark matter is made of, because many different substances could, in principle, produce the same gravitational influence. To move beyond gravity's message, scientists attempt to detect dark matter through non-gravitational interactions. They build detectors deep underground, shielded from cosmic rays, waiting for rare collisions between dark matter particles and ordinary atoms. They search for subtle excesses in particle collisions, for missing energy that might indicate new particles. They look to space for signals that could arise if dark matter annihilates or decays. These efforts belong to another part of the story, one that reaches beyond the sky into laboratories. Yet their existence reflects the same core fact. Gravity has done its job. It has pointed to something present. Now the search is for identity. For the purpose of our journey here, gravity remains the central narrator. It is the force that turns darkness into evidence. It teaches us how to know without seeing. In the end, perhaps the most serene lesson is this: the universe is not built to be understood through a single sense. Light is a gift, but it is not the full inventory. Motion is a clue, but it needs interpretation. Distortion is a map, but it demands patience. Gravity ties these together. It is the quiet thread that runs through brightness and darkness alike, shaping what exists, whether or not it can be photographed. And when we learn to read that thread, the cosmos becomes richer, not poorer. The darkness stops being empty. It becomes weight, structure, and history. An unseen architecture that holds galaxies together while leaving their starlight free to drift and shine. If you could remove every star from a galaxy, the galaxy would not disappear. Its light would be gone, and with it the familiar shape we recognize in photographs. But the motions that once traced that shape would still have a reason. The orbits would still want a center. The paths would still curve, as if something were there. In the universe, structure is not only what glows. Structure is what guides. On the largest scales, this guiding presence becomes easier to sense, not because it becomes visible, but because it becomes patterned. When astronomers map the positions of galaxies across immense volumes of space, they do not find a smooth sprinkling. They find filaments, long strands of galaxies and clusters woven into a web, separated by voids so wide they seem like deliberate absences.
The web has knots where clusters gather, bridges where matter appears to stream, and empty regions where almost nothing luminous resides. This arrangement can look, at first glance, like a property of galaxies themselves, as if galaxies simply prefer company in some places and solitude in others. But the more carefully the distribution is measured, the more it resembles the outcome of gravity acting on something deeper than the galaxies we can see. The web feels like a skeleton. The galaxies feel like the skin. To understand why, it helps to imagine the universe before the first stars, when there were no bright markers at all. In that early time, matter was not arranged into galaxies. It was a nearly uniform mixture, with slight variations, tiny differences in density that were small enough to be almost nothing, yet meaningful enough to become everything. Gravity has one essential habit. It amplifies differences. Where there is a little more mass, gravity pulls a little more strongly. That stronger pull draws in more matter, making the region heavier still. Over time, the slight becomes significant. The shallow becomes deep. A gentle dimple in the universe's density can grow into a well. But ordinary matter, the kind that later becomes stars and planets, does not fall into wells as freely as you might expect. It interacts with light. It heats and cools. In the young universe, when radiation was intense and matter was still entangled with it, ordinary matter was pressured and smoothed, kept from clumping too quickly. It could not simply collapse wherever gravity invited it to. A dark component, however, one that does not couple strongly to light, would not be held back in the same way. It would begin to gather earlier, quietly forming gravitational wells while the ordinary matter remained partly restrained. The result would be a universe where the first scaffolding is invisible. Broad halos and filaments of mass that deepen over time, preparing pathways for the luminous matter to follow. This is not an image we can point to directly. It is a story inferred from consistency, from the growth of structure, from the patterns in galaxy surveys, from the way gravity seems to have had help building complexity on schedule. In this view, galaxies are not the origin of the web. They are what happens when gas finally finds a place to settle. Ordinary matter, once the universe cools enough, begins to fall into these pre-existing wells. It streams along filaments, gathers in denser regions, compresses, and eventually forms stars. Where the dark matter halo is deeper, more gas can be captured. Where it is shallow, star formation may be modest or brief. The luminous universe becomes a tracer of the dark one, bright where the invisible framework is strong, sparse where it is weak. The calm strangeness of this idea is that it suggests a reversal of what the eye wants to believe. It is natural to think the bright objects create the structure, and the darkness is merely what lies between them. But the evidence implies the opposite. The darkness is the architecture, and the brightness is what collects inside it. As this architecture grows, it also shapes the history of collisions and mergers. Galaxies do not grow in isolation. They encounter one another, tug, pass, and sometimes combine. In those encounters, dark matter halos overlap and merge as well, creating larger gravitational domains that can hold more luminous matter. Over cosmic time,
This process builds clusters and superclusters, knitting the web into a more elaborate form. And yet, even as the scaffold explains so much, it leaves one central thing untouched: identity. A framework can be mapped, it can be weighed, it can be described in terms of how it behaves in gravity, but to ask what it is made of is to step into a quieter kind of mystery, one that sits at the border between astronomy and the physics of the very small. If dark matter is made of particles, they must be unlike the particles that form atoms. They must be long-lived, abundant, and reluctant to interact with light. They must pass through ordinary matter with an indifference that makes detection difficult. They must also fit within the larger logic of physics, not as a poetic addition, but as a stable ingredient that does not break what we have already learned in other domains. That is an unusually narrow set of requirements, and it is why the search has taken so many forms. Some possibilities imagine dark matter as heavy and slow-moving, shaping structure through its inertia. Others imagine it as lighter, perhaps behaving more like a vast, diffuse field. Some models aim to solve puzzles in particle physics while also accounting for cosmic structure. Others are driven purely by astrophysical necessity, hunting for the simplest, unseen mass that matches the gravitational evidence. Each possibility comes with a different kind of silence. A particle that almost never interacts could be everywhere and still leave no direct trace. A field could fill the universe smoothly, yet still clump gravitationally under the right conditions. A modification to gravity itself could mimic the influence of unseen mass in certain environments while failing in others. This is why the story remains active rather than closed. The scaffold is persuasive, but the universe has not yet handed us the material it is made from. Even within the gravitational framework, there are edges where the fit is less than perfect. Small tensions that do not undo the broader picture, but do remind us that the universe is subtle. The inner structures of some galaxies, the detailed distribution of satellites, the way dark matter appears to behave in certain small-scale environments, these details sometimes provoke debates about how the scaffold should look in its finer grain. They are not failures so much as invitations, evidence that the simple outline is correct, but the texture may still be unfinished. In that sense, dark matter is not only a missing piece of the universe, it is a missing piece of our own understanding of how nature builds. And then, slowly, the question of meaning arrives, not as a separate topic, but as a consequence of the picture. To live in an unseen universe is to live with the recognition that reality is not arranged for human senses. We are not at the center of the cosmos's composition. The matter that forms eyes and brains and stories may be a small fraction of what exists. The universe is not mostly the kind of substance that can think about the universe. This could feel alienating, but it can also feel clarifying. It removes a quiet arrogance that often hides inside the act of looking, the assumption that the visible is the main event. Instead, the universe becomes layered. The luminous layer, stars, nebulae, galaxies, remains extraordinary in its complexity. But beneath it lies a more massive layer that is simpler in its interaction, yet decisive in its influence. One layer provides the stage, the other provides the drama. Together they produce the world we can observe. And perhaps the most calming implication is that knowledge does not require direct sight to be real. We have always lived among invisible truths. We breathe a transparent atmosphere held by gravity we cannot see, guided by forces that announce themselves only through effect. The cosmic version of this is not a betrayal of understanding. It is an expansion of it. It asks us to accept that the universe's most important structures might be readable only through patience, through inference, through the quiet discipline of following what moves. The scaffold does not diminish the stars. It explains why the stars have somewhere to gather, and it suggests that the universe's deepest order may not be a spectacle, but a consistency. A steady, unseen weight that allows bright things to form, to persist, and to arrange themselves into patterns vast enough to be called a cosmos. The moment you accept an unseen scaffold, the universe begins to feel older. Not older in years, but older in character, like a place whose main structure was built before the decorations were ever imagined. The galaxies we admire become late arrivals, lights switched on inside a framework that had already taken shape in darkness. And with that shift comes a different kind of wonder. Not the wonder of what is visible, but the wonder of what has been quietly doing the essential work all along. This is why the story of dark matter does not end at the edges of galaxies. It keeps moving outward and backward into the conditions that allowed those galaxies to exist at all. In the early universe, the first traces of structure were small, and their growth depended on timing. If ordinary matter were left alone, coupled tightly to radiation, its tendency to clump would be delayed. Pressure from the surrounding light would smooth it out, resisting collapse. In that young cosmic environment, gravity needed a partner, something that could begin gathering without being pushed back by radiation. Dark matter, in the standard picture, plays that role. It begins to form wells earlier. It creates gravitational low points in the landscape of space, places where ordinary matter can later fall when the universe becomes cool and quiet enough. In doing so, it does not merely add extra weight. It sets the schedule of cosmic history. It affects when the first stars can form, how quickly galaxies can assemble, and how the cosmic web can become established. This is a subtle kind of power. It is not the power of producing light or heat. It is the power of shaping opportunity. And yet, despite how much the scaffold explains, there remains a nearly perfect emptiness at the center of the question. We do not know what it is. This is where the modern mystery lives, not in whether dark matter has gravitational influence, but in why it remains hidden from every other kind of interaction we routinely measure. If dark matter is a particle, it must be astonishingly reluctant to collide with ordinary matter. It must slide through atoms without scattering, drift through planets without leaving trails of heat, pass through detectors without disturbing their delicate quiet. It must be abundant enough to shape galaxies and clusters, but shy enough to remain uncounted in laboratories. This combination is unusual, but it is not logically impossible. Nature contains particles that pass through ordinary matter with ease. Neutrinos, for example, stream through Earth in vast numbers. We know they exist not because we can hold them, but because, with enough patience, we can detect their rare interactions. They are a reminder that the universe can be filled with things that barely touch us. Dark matter would be even more elusive. It would be a kind of presence that is not absent, but simply unresponsive to the electromagnetic world. To search for such a thing, scientists try to create places of extraordinary quiet. They build detectors deep underground, where the noise of cosmic rays is reduced. They use heavy shielding. They watch for tiny flashes, slight vibrations, minuscule releases of energy, anything that could mark a rare encounter between an unseen particle and an atomic nucleus. At the same time, other searches look outward. If dark matter particles can sometimes destroy one another or decay, they might produce faint signals in space, subtle excesses of radiation or particles that differ from known astrophysical sources. And in particle accelerators, physicists look for missing energy in high-speed collisions, as if a portion of the result has escaped into a new, invisible sector. So far, this part of the story has been defined as much by restraint as by discovery. Experiments have grown more sensitive, more carefully designed, more deeply isolated from noise. They have narrowed possibilities, closing doors that once seemed plausible. Each non-detection is not empty, it is information. It tells us what dark matter is less likely to be and how it must behave if it exists. In this way, the mystery sharpens. The unseen scaffold remains necessary for the gravitational story, but its identity remains out of reach, as if the universe is allowing us to map the architecture while refusing to hand us the building material. That refusal has consequences for our sense of knowledge. It teaches a particular humility, the humility of knowing that an explanation can be strong without being complete. It is possible to be confident in the presence of a phenomenon and still uncertain about its underlying cause. The universe, in practice, often separates these stages. It lets us learn what is true before it lets us learn why. This separation is not unique to dark matter. It is a common rhythm in science, repeating across centuries. But in cosmology, where we cannot conduct experiments on galaxies the way we can on liquids in a laboratory, the rhythm becomes more pronounced. We are forced to listen rather than manipulate. We are forced to accept that the universe may reveal itself only in the forms it chooses. Dark matter, then, becomes a lesson in method. It reminds us that the most reliable way to know the cosmos is not to demand certainty, but to build constraints, tight, overlapping, mutually reinforcing boundaries around what must be true. And within those boundaries, new possibilities remain. It is still possible that dark matter is a particle unlike any we have yet detected. It is still possible that it behaves more like a field. It is still possible that gravity, in certain regimes, behaves differently than we expect. Each of these ideas must face the same set of observations: rotation curves, lensing maps, cluster behavior, the growth of large-scale structure, the ancient patterns in relic light. The universe does not allow just any story. It allows only those that can survive many kinds of measurement at once. This is the quiet rigor of cosmology. It is not a field of speculation drifting freely in darkness. It is a field of hypotheses held tightly to a long chain of evidence. When you widen the view far enough, this rigor produces an unexpected kind of calm, because it means the universe is not arbitrary. Even in its hidden parts, it obeys patterns. It can be measured. It can be mapped. The unseen is not beyond comprehension. It is simply beyond direct sight. And once you accept that, the meaning of living in such a universe shifts gently. We do not inhabit a cosmos that is made for our senses, but we do inhabit one that can be understood by minds willing to extend those senses with instruments and patience. The night sky, in this perspective, becomes a surface layer of a much deeper reality. The stars remain real, but they are no longer the whole. They are the luminous trace of a gravitational story written in darkness. There is also a more intimate implication. Our own existence may depend on this unseen scaffolding. If dark matter shaped the formation of galaxies, then it shaped the environments where stars could form. And if it helped gather the gas that became stars, it indirectly helped create the heavy elements those stars forged, elements that later became planets, oceans, and living chemistry. The scaffold did not create life, but it may have made the conditions for life more likely by making structure possible at the right time. In that sense, the unseen is not a distant abstraction. It is part of the deep history that leads, eventually, to a human being looking up and asking what holds the universe together. And perhaps that is the most quietly profound turn of the story. The universe is held by something we cannot see, and yet we have become the kind of matter that can notice. Not by accident, but by the long accumulation of structure shaped by gravity, guided by an invisible weight, and lit, at last, by stars. The cosmic scaffold remains unseen, but it is not unknowable. It is present in every orbit that stays bound, in every filament of galaxies stretched across space, in every lensing arc that bends a distant light. It is a reminder that reality is deeper than the bright layer we first fall in love with. And in that depth, the universe feels less like a stage set for observation and more like a true place, vast, structured, partly hidden, and patiently revealing itself to those willing to listen beyond what the eye can immediately confirm.